4 of class 11 physics. It is the famous laws of motion. Now let's start with this. Okay. Laws of motion, chapter 4 of class 11 physics. The concepts in these topics are Aristotle's fallacy, the law of inertia, Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, conservation of momentum, equilibrium of a particle, common forces in mechanics, circular motion, solving problems in mechanics. That is summary of points to ponder, and then exercises. Let's start with first topic 4.1 introduction. In the preceding chapter, the straight lines chapter or planes chapter, basically kinematics, in the preceding chapter our concern was to describe the motion of a particle in space quantitatively. What we did in our preceding chapters, we did that we described the motion of a particle, the moving of a particle in space, in free space, in a three-dimensional space, quantitatively meaning in terms of magnitude and in terms of how much fast it is moving or how much slow it is moving. Basically, that is what it means. We saw that uniform motion needs the concept of velocity alone, whereas non-uniform motion requires the concept of acceleration in addition. Basically, we have uniform and non-uniform motion. In uniform motion, we have speed and velocity. But in case of non-uniform motion, we need to define speed, varying speed or varying velocity. So we brought a new concept called as acceleration. How much speed is increasing or how much velocity is increasing per unit time, or how much it is decreasing per unit time. That is what we call it as acceleration. So it is the second concept introduced, that is in non-uniform motion. So far, we have not asked the question as to what governs the motion of bodies. Okay, like we know that in the before chapters, we know the body is moving, we know the body is at rest, but we don't know how it is moving, we don't know how it is at rest. But now, in this chapter, we turn to this basic question. How is it moving? Now, let us first guess the answer based on our common experience. Okay, to move a football at rest, someone must kick it. Yes, when you play soccer or football, you need to kick the ball for it to move or fly or make a goal. And to throw a stone upwards, one has to give it an upward push. They're basically saying that we should throw the stone. Otherwise, it won't move. We should give it a push. That is what we call throwing. A breeze causes the branches of a tree to swing. A strong wind can even move heavy object. Wind energy, wind turbines, windmills, they move through wind only. A boat moves in a flowing river without anyone rowing it. This is not talking about the wind forces here, they're talking about the moving water in a flowing river they mentioned. In a flowing river, the boat moves. And if we observe, normally if there is no force acting on them, they wouldn't have moved. So clearly we can say some external agency is needed to provide force to move a body from rest. Some external agency, whatever it might be, should provide the force to move the body. Likewise, an external force is also needed to retard or stop the motion. If its object is moving, if we want to stop that object, we need some force. To move it also we need to apply some force. To stop it also we need to apply some force. You can stop a ball rolling down on an inclined plane by applying a force against the direction of its motion. Okay. In these examples, the external agency of force, hands, winds, stream, etc., is in contact with the object. This is not always necessary. Basically, in whatever examples we saw here, where the boat was moving due to water current, the stone was moving due to pushing the stone or throwing the stone with our hands, and the football was flying because someone kicked it. In this case, the force we applied was in contact with the object. The foot and the ball, the hand and the stone, the water and the boat, all in contact with the object that is moving. But this is not always necessary. Like a force doesn't always need to be contact force. It can also be applied without a contact. A stone released from the top of a building accelerates downward due to gravitational pull of the earth. We say gravity. Gravity is the gravitational pull. We don't see hands pulling the object down. We don't see any kind of earth coming up and pulling the ball down or something like that. There is nothing like that. But still, we can say that there is a gravitational pull, and this is an example for force without contact. And if we see a magnets, a very famous example, no, a very popular example, a bar magnet can attract an iron nail from a distance. Bar magnet can attract an iron nail from a distance. This shows that external agencies, basically external forces, that can be gravitational force, magnetic force, or even in 12th standard we are going to see about electric forces as well, can exert force on a body even from a distance. Even from a distance, they can apply a force. In short, a force is required to put a stationary body in motion or stop a moving body. Basically, they are saying, basically, whatever we saw here is, for a body to go from rest to motion, we need to apply a force. For a body to go from motion to rest, we need to apply a force. For a body to go from rest to motion, we need to apply a force. For a body to go from motion to rest, we need to apply a force. The force can be through contact or without contact with the object. Now let's go to the next page. Not here, but in the NCERT, we still have something left. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. Some external agency, whatever it might be. In case of gravitational force, it is the earth. In case of magnetic force, it's the magnet. That is what we call an external agency, which is providing the force or applying the force. The external agency may or may not be in contact with the body. So far, so good. I hope so. But what if a body is moving uniformly? Example, skater moving straight with a constant speed on a horizontal ice slab. Ice slab meaning frictionless slab. Is an external force required to keep a body in uniform motion? Do you think so? If in reality, ice slab is not completely frictionless, so the skater will indeed stop, but in an ideal frictionless slab if a skater is indeed moving in a straight line with a uniform velocity. Unless someone is there to stop him, he will continue to go for no matter how long, until he lives, I guess, for infinity. That's what they're saying. Basically, they're saying as long as this is a frictionless surface, if a skater is going, he will continue to go unless someone stops him. Three wheels for a skater, fine. A fancy skateboard. Anyways, the second topic, Aristotle's fallacy. The question here, they said, is an external force required to keep a body in uniform motion? The question here appears to be simple. However, it took ages to answer it. Okay, maybe we missed something here. They're asking, is an external force required to keep a body in motion? Should we keep applying the force always, or once if we push the skater, once the skater is pushed forward, then it is enough, or we need to continue pushing the skater? That is the question they're asking. We know the answer, that we only need to push the skater once so that the skater can continue to move in uniform motion. This question posed above appears to be simple, however, it took ages to answer it. Indeed, the correct answer to this question was given by Galileo in the 17th century, was the foundation of Newtonian mechanics, which signaled the birth of modern science. Basically, the above answer was given by Galileo, the one who discovered the telescope, basically. And this answer became the base of the foundation of Newtonian mechanics, basically Newton's laws, which signaled the birth of the modern science. The Greek thinker Aristotle, 384 BC to 322 BC, held the view that if a body is moving, something external is required to keep it moving. According to this view, for example, an arrow shot from a bow keeps flying since the air behind the arrow keeps pushing it. The view was part of an elaborate framework of ideas developed by Aristotle on motion of bodies in the universe. Basically, the Greek thinker Aristotle, 380, held the view that he thought that if a body is moving, something external is required to keep it moving. He is telling something opposite of what I told before, but I told that in a frictionless surface, meaning there is no external force acting on the skater. The skater here will continue to move forward with uniform velocity when there is zero force acting on it, be it be frictional force, be it be air resistance, or anything like that. It can only go for infinity distance only when there are no external forces acting on the body. But at the time, Aristotle, he held that the body moving, something external needed to keep it moving. External force is required to keep it moving. That's what he thought. In this view, according to his view, for example, an arrow shot from a bow keeps flying since the air behind the arrow keeps pushing it. Okay, fine. The view was part of an elaborate framework of ideas developed by Aristotle on the motion of bodies in the universe. Most of Aristotelian ideas on motion are now known to be wrong and need not concern us We don't need to read about them. For our purpose here, the Aristotelian law of motion may be phrased thus. Aristotelian law of motion may be phrased thus. An external force is required to keep a body in motion. Okay, that is the law here. Aristotelian law of motion is flawed, meaning it is wrong, or some problems are there here. As where the problem is there, this is the law. An external force is required to keep a body in motion. That is law here. Now we will see where the problem is. We know it is wrong. We will see where the problem lies. However, it is a natural view that anyone would hold from common experience. Basically, this is kind of everyone will know. Everyone basically who doesn't read the 11th standard physics textbook generally will think that this is the case. An external force is required to keep a body in motion. When we push the skateboard or any kind of toy car on the ground, when we push it, it will obviously come to a stop. It will not go for infinity and infinity. It will come to a stop in a finite distance when we push a toy car on the ground. So obviously people will think that we need to apply an external force to keep the body in motion. If we keep pulling the car, then it will be in pushing the car, then it will be in continuous motion. That is common experience. Even a small child playing with a simple non-electric toy car on a floor knows intuitively that it needs to constantly drag the skin attached to the toy with some force to keep it going. If it releases the string, it comes to rest. Basically, yeah, that's what example I said. This experience is common to most terrestrial motion. This example, this is people walk on the ground, so it is mostly common, like we terrestrial life forms. It is common experience for us. We see in many things. External force seems to be needed to keep the body in motion. Left to themselves, all bodies eventually come to rest. This is what we see, common experience. Now let's see what is the flaw in Aristotle's argument. The answer is a moving toy car comes to rest because the external force of friction on the car by the floor opposes its motion. That's what I've been talking about of frictional forces. Basically, when a moving toy car, when we push it, it comes to rest only because of other force acting on it, that is the frictional force on the ground. And to counter this frictional force, the child has to apply an external force on the car in the direction of motion. Basically, if he wants the car to be moving, he need to oppose this frictional force. And he need to like apply a greater force than the frictional force to keep the car moving. That is basically pulling the car. And when he is pulling the car, the frictional force is not enough to stop the car, so the car will move. When the car is in uniform motion, there is no net external force acting on it. Basically, when the car is in uniform motion, there is no net external force acting on it. That is the only reason it can be in uniform motion only if there is no, it can only be in rest, or it can only be in motion, uniform motion, that is when the net force acting on the car is zero, or the toy is zero. Basically if there is a car and if it is going in uniform motion, then if one thing, there should be no force acting on it. Force should be zero. Force acting on car should be zero. There's no force acting on it. No one is applying force on it. Then it will continue. The first case is when there is no force acting on this car, it will continue to stay in motion. The second is when there is the net forces acting on it is zero. Basically, The friction, if the car is moving in this direction, the friction force will act on this direction, then it will come to a stop. So to continue the car from going continue for the car to continue to go in uniform motion, we need to apply an equal and opposite force external, that is force of pulling, the boy pulling the car. So we can say F pulling the car should be equal to F friction. Then only the car will remain at uniform motion. That is what they mean. The net force is the total force acting on the car. Since it is in this direction and this is in this direction, Fp minus F friction equals 0. Fine, it's taking too much time. Anyways, the force by the child cancel the force friction by the force of the pulling is applied by none other than the child, and the the corollary is that if there were no friction, the child would not be required to apply any force to keep the toy car in motion. If there is no opposing force, once if we push the car or if it's already in motion, then nobody's stopping it. Then why would we need to continue to apply the force? There is no opposing force. So by applying external force, it will only get accelerated. It will, even without applying force, it will continue to move because there is no opposing forces. The opposing forces such as friction in case of solid, viscous forces in case of liquids are always present in the natural world. In the real world, we will always see forces such as friction, force in case of frictions in case of solid. The same thing, viscous friction in water is called as viscous force. It is kind of similar like that. These are always present in the real world. If you see, this will always be present. This explains why forces by external agencies are necessary to overcome the frictional forces to keep bodies in uniform motion. That is explain the laws, like Aristotelian law said that an external force is required to keep a body in motion. That is what Aristotle said. We know that in the real world we have friction and viscous forces. That is the reason we need to apply force, continue to apply force in a real world to keep the bodies in uniform motion. Now we understand where Aristotle went wrong. He didn't know about the friction, he didn't know about the viscous forces. He just thought that it must be the case that in all places also this is the case. In all places also there must be always force to keep the body moving. He coded this practical experience in the form of basic argument. Basically, whatever his law is, he just made it so that people can understand in a practical experience. That is a basic argument. To get at the true law of nature for forces and motion, one has to imagine a world in which uniform motion is possible with no frictional force opposing it. This is what Galileo did. Basically, how nature of forces act and how force can induce motion, this is something we can only truly find out in a world where there is no friction or any kind of opposing forces, where the uniform motion, which seems very hard, at least at that time in the real world, is only possible in the fictional world or the ideal world. So when we did that, that is what Galileo did, and he came up with the answer to the above question, that is is an external force required to keep a body in uniform motion. He did it. He imagined an ideal world. He succeeded in answering the question. Is an external force required to keep a body in motion. Now let's see the next main topic of 4.3, the law of inertia. Galileo studied the motion of objects on an inclined plane. Okay. Basically, the law of inertia topic. Basically, we are talking about Galileo here. Galileo, he studied motion of object, moving of object in an inclined plane. Inclined plane is nothing but like a slide or a slope, where if we put a ball in a slope, it will continue to move down. That he studied. Objects, one, first thing he studied, moving down an inclined plane, accelerate. Basically, when things are moving down an inclined plane like this here, the ball is moving down, they accelerate. Accelerate meaning they do not go in uniform motion. Their velocity increases as it goes down the slide. It is moving faster at the end of the slope compared to at the starting position. While exactly opposite, the objects moving up slow down or retard, basically deceleration, basically minus acceleration. Acceleration where the speed is reducing. And third, objects motion on a horizontal plane is an intermediate situation. Basically, in case of this is the going down a plane, this is the going up a plane, where this continues to increase velocity, this continues to decrease velocity. In case of a horizontal plane, we see that it is middle of these two. It is not completely accelerating, it is not completely decelerating, it is in the medium. It is slowly decelerating. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor deceleration, that it should move with constant velocity. But this is not actually true. It's just how we can imagine. We imagine that if it goes down a plane, it should increase in velocity or acceleration should be there. When it goes down the plane, like it goes from up to down a slide, then velocity should decrease like this. It should increase here, it should decrease here. So obviously people will think that when it is moving like this, it should be in constant velocity, right? That is also the thing Galileo also thought. Galileo concluded that when an object is moving on a frictionless horizontal surface or a plane, object must wait. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation. Okay. He considered frictionless here. Frictionless means whatever he said is correct. In a frictionless horizontal plane, when there is no friction acting on it, there should be no acceleration, there should be no deceleration or retardation. The body should move in a uniform, constant velocity. That is what he concluded. It is indeed correct. That is only for a frictionless surface. When we have friction as a factor, then we cannot say it is true, because at initial we have some velocity, it is moving very fast. When we roll down a bowling ball, at the end, after some time, it will come to a stop. So it is not uniform velocity. But in case of a frictionless surface, it is indeed true that it will go in uniform motion. Another experiment by Galileo leading to the same conclusion involves a double inclined plane. Okay, he did one more experiment where it was a double inclined plane. A ball is released from the rest on one of the planes, where the object rolls down and climbs up the other, basically like this. This is the plane. This is the double inclined plane. Here, if we release the object here, then of course it will roll down, it will climb this again like this. It will be a motion like that. If planes are smooth, the final height of the ball is nearly same as the initial height, a little less but never greater. Basically, what he meant by smooth here, basically here, um, here smooth. Smooth means obviously frictionless planes. When these inclined planes are frictionless, the ball will come here, and in case of the real world it will be a little less down here. The ball will come down here, or in case of an ideal frictionless world, it will come exact height. If this is h height, this will also h height. That is what he's saying. And in case of if there is, we can say, in case of the real world, we do not have perfect ideal frictionless bodies, so it will be here in case of a very smooth plane, but it is never here. We can never say that it is higher than the initial height. It will always be just yes. Let's continue. Okay, where yes, another experiment by Galileo leading to the same conclusion involves a double inclined plane. A ball released from the rest on one of the plane rolls down and climbs up the another. This diagram here, and the final height of the ball is nearly, in case of a smooth surface, the final height of the ball is nearly the same as the initial height, a little less but never greater. In the ideal situation, when friction is absent, the final height of the ball is the same as its initial height. If the slope of the second plane is decreased and the experiment repeated like this, where the slope is decreased, the ball will still reach the same height. Even though the slope is less, it will still reach the same height. That is in an ideal frictionless surface. But in doing so, it will travel a longer distance. Basically, here, basically in, let's see here, let's do the same experiment here. Um, Experiments of Galileo. The experiment is basically mm, let's take like this. It's like a beaker, but it's not like a beaker. Should not be like a beaker. From it's not the diagram is not coming well. Let's not do this. Let's see in textbook only. I think textbook is better. Anyways, basically this is the slope here. Let's use the highlighter. This is the experiment. In this case, when the slope from the previous chapter, we calculated or we know to calculate the slope of any kind of plane. We take a tangent here when we know that the slope here will be equal to the slope here. The slope here will be equal to the slope on the left hand side as well. That is, in this case, the here also the same height is reached. In one more case where the slope in the left hand side is greater than the slope on the right hand side, where this is a lesser slope, then also when we release a ball in a perfectly ideal world, frictionless world, there will still be reaching the same height. It will be reaching the same height. But if we see the distance, if we see here, the distance, if we take this as x and this as x dash, x will be greater than x dash. Meaning basically that x will be greater than x dash. That is what they are saying here. That is what they are saying. In doing so, it will travel a longer distance. In the limiting case, when the slope of the second plane is 0, like this, that is a horizontal, the ball travels an infinite distance. In a frictionless plane, there is no for stopping the ball, so it will continue to go. In here as well, it will continue to oscillate like this. It will continue to go up and down and up and down as long as there is no friction for infinity. The ball will continue to move up and down and up and down. Here as well, the ball will not go up and down, but in this case, it will go horizontal for infinite distance. In other words, its motion never ceases. This, of course, is an idealized situation, which is a very ideal situation. The law of inertia was inferred by Galileo from observation of a motion of a ball on a double inclined plane. But in practice, if we see, the ball does not come to a stop after moving. Does not. It in practice, in reality, in real world situation, the ball does come to a stop after moving a finite distance on the horizontal plane. After moving some distance, it will come to a stop because of the opposing force of friction, which can never be totally eliminated. In real world, it is very hard to eliminate friction completely. However, if there were no friction, the ball would continue to move with a constant velocity on the horizontal plane. Galileo thus arrived at the new insight on motion that had eluded Aristotle and those who followed him. Okay, the state of rest and the state of uniform linear motion, motion with constant velocity, are equivalent. In both cases, there is accomplished a single-handedly by Isaac Newton, one of the greatest scientists of all time. Basically, Galileo gave that law. He observed the inertia first and the state of rest. The law is the state of rest and the state of uniform linear motion are equivalent. Basically, The state when the body is in rest, then the body is not in moving, then also the total force on the body is zero. When the body is moving in uniform motion, linear uniform motion, then also the net force on the body is zero. That is what they're saying here. When the body is in rest, when the body is in uniform motion, the net force on the body is zero. That is what they mean by state of rest and state of uniform linear motion. That is motion with constant velocity are equivalent. In both cases, there is accomplished almost single-handedly by Isaac Newton. That is, more about these states was mostly given by Isaac Newton, one of the most greatest scientists of all time. Newton Newton basically built on Galileo's ideas and laid foundations of mechanics in terms of three laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Basically, Isaac Newton, built on Galileo's ideas. Whatever Galileo said, based on that, he started his research and he built on Galileo's ideas. And his first law was the law of inertia, which is basically Galileo's law of inertia was his starting point, from which he formulated as the first law of motion. Goes by the three laws he gave, goes by his name, the Newton's laws of motion. And okay, and the first law states that every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. Let's read the statement again. This is the first law of motion, Newton's first laws of motion. Every body, every object, every body continues to be in a state of rest or in a state of uniform motion. Point to pay attention, uniform motion in a straight line unless compelled by some external force to act otherwise. Here we say it's a straight line because we are dealing with vector quantities here. And even if the magnitude of force is zero and the direction is different, it is not constant force. Now they gave some extra information here. Ideas of motion or on motion in ancient Indian science. Okay, let's see. Ancient Indian thinkers, let's just read it once. Ancient Indian thinkers had arrived at an elaborate system of ideas on motion. Okay, they came up with many things. Force, the cause of motion, was thought to be different kinds. Force due to continuous pressure, Nodan, as the force of wind on a sailing vessel. Impact, Abhigat, as when a potter's rod strikes the wheel. Persistent tendency, Sanskara, to move in a straight line, Vega, or restoration of shape in an elastic body. Transmitted force by a string rod, etc. The notion of Vega in the Vaiseka theory of motion perhaps comes closest to the concept of inertia. Basically, this given by the notion of Vega in the Vaiseka theory of motion, this comes closest to the concept of inertia. Vega, the tendency to move in a straight line, was thought to be opposed by contact with objects including atmosphere. Basically, they are talking about here the frictional atmospheric forces like air resistance, or viscous forces like water forces, water resistance like resistance forces like water resistance, we can say, etc. A parallel of the ideas of friction and air resistance. That's what I said here. Air, water, friction. I'm not sure if they talked about water here, but they did mention air resistance and water friction here. Friction meaning solid objects, solid to solid contact. They said here that opposed by contact with objects. It was correctly summarized that the different kinds of motion, translational, rotational, and vibrational of an extended body arise only from the translational motion of its constituent particles. Basically, they are saying that different kinds of motion. We saw many kinds of motion in our preceding chapters, in our not preceding, previous chapters. In these motion, we saw translational motion, motion in straight line, rotational motion, vibrational of a body arise from only the translational motion of its constituent particles. A falling leaf in the wind may be downward motion as whole pattern, and also rotational and vibrational motion Brahman and Spandan, but each particle of the leaf at an instant only has a small displacement. Okay, we can describe any kind of motion in kinds of small lines of translational motion. Translation motion is nothing but straight line. Basically, if we have a curve like this, we can divide it into many kinds of straight lines based on slopes or anything like that. Basically, they are saying that any kind of motion here can be described in terms of small amounts of translational or straight line motion. There was considerable focus in India taught on measurement of motion and units of length and time. It was known that the position of a particle in space can be indicated by distance measured along 3 axes. This was also known that the position of a particle in space can be indicated by distance measured along 3 axes, the x, y, and z. Basically, this is basically 3-dimensional that imagining right here. Bhaskara 1150 AD had introduced the concept of instantaneous motion, Tatkaliki Gati, which anticipated the modern notion of instantaneous velocity using differential calculus. Basically, instantaneous motion, we know the particle in basically average. We have two kinds of motion. We have average and instantaneous. Average motion, or average in case of speeds if we take, or velocities if we take, we have average velocity and average, not average, instantaneous velocity. Instantaneous in average velocity, we took change in distance by change in time. This is for V average, and this time interval is large time interval. But V instantaneous, we take limit delta t tends to 0 dt, actually dx by dt, where this time interval is extremely minute and it is very close to 0. That is what they talk about instantaneous motion. Instantaneous motion, the velocity there is, we can take it as a constant. At an instant, at a very minute instant, the particle will be moving at constant velocity at that interval of time. The difference between a wave and a current of water was clearly understood. A current is a motion of particles of water under gravity and fluidity, while a wave results from the transmission of vibration of water particles. Basically, they understood what the difference between flowing water currents and a wave. When we throw a stone into a lake or something, a calm lake, we see many kinds of ripples, or I don't know what they call it, but basically waves in the water. The difference between them is that water is due to flow of particles, continuous one directional flow of particles, but a wave is different from a current. Current is a transmission of vibration of water particles. Okay, that is basically ideas on motion, that is in ancient Indian science. Now let's come back to our chapter here. It seems I read this. Okay, yes. Okay. It seems there is no connection here, but let's erase this one. This continues not from here, but from here. In both cases of linear motion with constant velocity and state of rest, in both cases, there is no net force acting on the body. That is what I said. It is incorrect to assume that a net force is needed to keep a body in uniform motion. We are basically giving the policy or the flaw in Aristotelian law. That is, it is incorrect to assume that a net force, we need to keep a net force acting on the body, that is to keep it in uniform motion. That is not always true. In the real world, it is mostly true, but not in the ideal world where friction is zero. To maintain a body in uniform motion, we need to apply an external force to basically counter the frictional force, so that the two forces sum to zero and the next sum up to zero and the net external force is zero. When the next external force is zero, the body will continue to move as it should be, moving with uniform velocity, or it can just stay at rest. To summarize, if the net external force is zero, a body at rest continues to remain at rest, and a body in motion continues to move with a uniform velocity. So the entire summarization is that if the net external force is zero, then a body at rest, a body not moving, a body at rest, this body at rest will continue to stay at rest, and a body that is moving will continue to move with a uniform motion. This property of body or an object, this is called as inertia, inert nature. That is, inertia means resistance to change. It's very conceptually, understanding wise, very important to remember that inertia means resistance to change, tendency of the object to resist change in its state of motion or state of rest is called as inertia. A body does not change its state of rest or uniform motion unless an external force compels to change that state. Now let's see the next main topic, that is Newton's first laws of motion. Galileo's simple but revolutionary ideas dethroned Aristotelian mechanics, and new mechanics had to be developed, and this task was accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all time. Basically, after Aristotle came Galileo. Now, Galileo gave the law of inertia. Now, what next? This next was almost single-handedly given. What next is given mostly by one of the greatest scientists of all time, that is Isaac Newton. Newton built on Galileo's ideas and laid foundation of mechanics in terms of three laws of motion that go by his name, that is Newton's laws of motion. Galileo's laws of inertia was his starting point, which he formulated as the first law of motion. Every body continues to be in a state of rest or uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both imply zero acceleration. The state of rest or uniform linear motion, both these states imply zero acceleration is there on the body. The first law of motion can therefore be simply expressed as if the net external force on a body is zero, its acceleration is also zero. Acceleration can be non-zero only if there is a next external force acting on the body. Okay. Two kinds of situations are encountered in the application of this law in practice. That is, in some examples, we know that the net external force on the object is zero. In that case, we can conclude that the acceleration of the body is zero. Okay. First, they are saying that if the net external force on the body is zero, then we can say acceleration of the body is zero. That is exact repeat of whatever we saw here. Exact same statement they are saying again here. Net external force on a body is zero, its acceleration is zero. Acceleration can only be non-zero if the net external force on the body is not zero. For example, a spaceship out in interstellar space, far from all other objects and with all its rockets turned off. This has no net external force acting on it. We took interstellar space, and not only space here, because interstellar is far away from many objects, many planets, away from any kind of force experience, any kind of net external force. That is why we took the interstellar space here, very far away from Earth, but a good example. In this case, there is no net external force acting on that spaceship because the rockets are also turned off. Then its acceleration, according to this first law of Newton, must always be zero. Must be zero basically. If it is in motion, it must continue to move with a uniform velocity. If it's in a state of rest, it will stay in the state of rest. But if it's in motion, then it will continue to move with the same velocity. Okay. More often, however, we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, that is, it is either at rest or in uniform linear motion, we can infer from the first law that the next external force on that object must be zero. Basically, they are saying that if we know that the object is unaccelerated, it's not accelerating, it's not changing in velocity. If they say unaccelerated, it obviously means uniform linear motion, and it is either at rest or in uniform linear motion. We can infer from the first law of inertia or the first law of motion that the next external force, then when the body is unaccelerated, the net external force on that body or that object is zero. Gravity is everywhere. Even in interstellar space, there will be gravity, but gravity is already a very weak force. The weakest force in nature is gravity. So when the distance is very far, the force is almost negligible. So that is why, even though in reality there is no place where is actually net zero force, there is always a force, but the total the force is very negligible, very small. Gravity is everywhere. For in the land, if we say terrestrial phenomena, in particular, every object experiences gravitational force due to Earth. On our Earth, on our planet, everywhere we see that every kind of object, any kind of object with mass will experience a force, that is the gravitational force. Also, objects in motion generally experience friction, viscous drag, etc. And objects in motion also generally experience friction, viscous drag. These are forces, opposing forces we saw before. If then on Earth an object is at rest or in uniform motion, linear motion, it is not because there are no forces acting on it, but because the various external forces cancel out, that is, add up to zero, net external force. Basically, as I said before, Mostly there is no place where force is zero. It is only negligible. Negligible on in our planet. If we see in our planet, if we see, if we think this is a block, it is resting on the ground. That is only because all the forces, there are forces acting in this direction, in this direction, in this, many kinds of forces are acting. But since force is a vector quantity and not a scalar quantity, these forces, when there is a force this side and a force this side, both are F Newton of forces. Then in this case, if there is an object in middle, the total force F net on the object will be zero. This is because force is a vector quantity and these forces cancel out. And that is the only reason in Earth where even though there is no chance where the object is not actually feeling any kind of force, the reason objects can be in rest on Earth is because the net force is zero. That is what they said here. Consider a book at rest on a horizontal surface, like here, this figure. It is subject to two external forces. It is subject to meaning two external forces are acting on it. The first force is gravity, because the book has a mass and everything that has mass will experience a force of gravity acting downward, and the next force acting on it is the upward force on the book by the table, the normal force R. Basically, if we think more about this book on a table, we know that we know the answer intuitively, but they're explaining it more about it here. Basically, they're saying a book is on a table. It has a mass, so it's experiencing a gravitational force. This is, let's call it Fg. If that is the case, shouldn't the book should like wouldn't the book fall down? Why is it just staying on a table? If it's experiencing a force, it should be falling down, but it's not falling down. We know the answer intuitively. Intuitively, we can say. We know it is not falling down because there is a table here. The table is there, so the book is not falling down, even though there is a force acting on the table, acting on the book. So does that mean the table is exerting a force this side that is equal to the F table is equal to the Fg, that is in magnitude. Uh, the table is basically the stopping the book from going down, falling down, and going with full acceleration toward the center of the earth. What is stopping it is the table. The table is putting a force in the upward direction. This force is called as the normal force, Fn, where Fn in magnitude will be equal to the Fg. Okay. Let's continue. It is subject to two external forces, that is force due to gravity, that is its weight acting downward, and the upward force on the book by the table, the normal force, not N here but R. R is a self-adjusting force. Basically, if the book was 1 kg and the force experienced on the book is some Newton due to gravity, then the force, if the table is very steady, meaning very rigid, it can support the weight of the book always, then it will apply also the same force. If the book is 1000 kg, the force experienced by the book is by the first book, which is 1 kg, will be smaller than the second book, which is the 1000 kg. So the normal reaction should also, if the table is still supporting the book, then the normal force acting on the book should be greater in case of the second case where the book was 1000 kg. So that is why they are calling R the normal force to be a self-adjusting force. It will increase if the book's force increases. If let's assume the book here is 1 kg, but for some reason the book reduced in weight to half of its weight normally, then the force acting downward will reduce. The force acting before will reduce. If let's assume the normal force acting upward, this will remain same, then the normal force should be greater than the gravitational force. Won't the book fly upward then? If the normal force acting on the normal force acting on the book is greater than the gravitational force, then the book will of course fly upward. It will just go up into the sky. That doesn't happen here. That is because it is a self-adjusting force. When the gravitational force decreases, the normal force is also decreasing. When the gravitational force increases, the normal force also increases. This is a self-adjusting force. This is an example of the kind of situation mentioned above. The forces are not quite known fully, but the state of motion is known. We do not know what kind of forces are acting because we can't see the forces. But we do know if the book is in motion, if the book is in rest, or what kind of motion the book is in, or the car here in the second case. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of the normal force, that is equal to the W, this is the gravitational force. A statement often encountered, since W equals R, forces cancel and therefore the book is at rest. W is the gravitational force, R is the normal force. Both are equal, both cancel out because force is a vector, and the book is at rest. This is incorrect reasoning. The correct statement is, basically we do not know the forces. Actually, we cannot say that W equals R, force cancel out and the book is at rest. We don't know, we don't see the forces. We don't see arm or pointing downwards or upwards that the force is this much and they are cancelling out. We cannot see that. We cannot see the forces. So what we can see is, since the book is observed to be at rest, the next external force on it must be zero according to the first law. This implies that normal force R must be equal and opposite to that of the weight W. This is what we can say from the first law. As we do not know the forces, but we do know is the state of motion of the state of rest of the book. So the correct statement is, since the book is observed to be at rest, we know the value we know is that, or the thing given to us is that the book is at rest. So the net external force on it must be zero. If the net external force on it must be zero, means we know that there is a force, gravitational force acting on it downward. So, and we also know there is a normal force acting on it upward. So if the net external force is zero, this implies that the normal force must be equal to the weight, we can say gravitational force. A is an example of a book at rest and B is an example of a car moving with uniform velocity. A net force is zero in both the cases, or in each case, which means the same thing. Consider the motion of a car starting from rest. A car is starting from rest, picking up speed, accelerating, and then moving on a smooth straight road with uniform speed. A smooth straight road. They are giving us the conditions here, that it is a frictionless surface and it's a translational motion, which is straight line. straight line motion. That is, when the car is stationary, there is no net force acting on it. When the car is not moving, there is no net force acting on it. During pickup, which is from zero velocity to whatever v velocity it is, its final velocity. During this pickup of speed, it accelerates. It's accelerating here. It's accelerating. Then what we can assume is this must happen. This acceleration is happening due to a net external force. Acceleration is happening due to a net external force. Notice it must be an external force. The acceleration of a car cannot be accounted for any internal force. They're saying the acceleration of car, this acceleration of car is due to an external force. It's not due to an internal force. But we see that the tires are the one moving, right? The tires are the one which are rotating and they are the one pushing the car forward. So should not that be considered as an internal force? Why are they saying it is an external force? This might sound not subscribing. It is surprising. But this is true. The only conceivable external force along the road is the force of friction. Okay, it is a frictional force that accelerates the car as a whole. Basically, let's assume we think that the tires of a car are the one doing the force here, so it should be an internal force. Let's assume it is a completely frictionless. No, wait. Okay, it's a completely frictionless road. If it's a completely frictionless road, then even if the tires rotate, do you think the car will move forward? Imagine a car on ice. When the car tires move, the car will not move. The tires will be free rolling, we can say. But the car will be stationary. The car will remain on rest, but the tire will be rotating. So the car will not move when the tires are moving, but it's only happening that the car is moving because of friction on the floor or friction on the road. When the tires are moving, the friction is pushing the car forward. It's applying the external force on the car. This will be talked more about in the section of 4.9. When the car moves with constant velocity, there is no net external force. If the car is moving with constant velocity, then there is no external force. The property of inertia contained in the first law is evident in many situations. In most of the situations we see, if we can relate it to the law of inertia. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backward with a jerk. Why? Our feet are in touch with the floor. If there was no friction, we would remain where we were, while the floor of the bus would simply flip under our feet and the back of the bus would hit us. However, basically, when we are standing in a bus, the bus suddenly picks up speed or starts from rest and accelerates, we jerk backward. This happens because fortunately there is some friction between us, the feet and the floor. If the start is not too sudden, that is, the acceleration is moderate, the frictional force will be enough to accelerate our feet along with the bus, but our body is not strictly a rigid body. It is deformable. That is, it allows some relative displacement between different parts. Basically, they are saying about our body flexibility here. What this means, why they are referring to flexibility here, is that while our feet go with the bus due to friction, the rest of the body remains where it is due to inertia. If it's a completely rigid body, it would not happen. We won't jerk backward if it's a completely rigid body. It is not a rigid body. Our body is not a rigid body. That is the reason we will continue to move. We will jerk backward when the acceleration is high. Related to the bus, therefore, we are thrown backward. As soon as that happens, however, the muscular forces on the rest of the body by feet come into play to move the body along with the bus. Okay, a similar thing happens when the bus suddenly stops. Our feet stop due to friction, which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. We are thrown forward. The restoring muscular forces again come into play and bring the body to rest. Basically, we jerk backward, but we do not completely fall down. We know that we will continue to be in motion if there is no net external, if there is no force acting on us. So which kind of force will act on us to stop us from falling down? That they said it's the muscular forces. Our body's muscular forces stop us from falling down. Okay, let's see the example here. An astronaut accidentally gets separated out of his small spaceship, accelerating in interstellar space at a constant rate of 100 meter per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. When he comes out, the instant, it should be zero, right? I think so. Yes, it is zero. Since there is no nearby stars to exert gravitational force on him, and the small spaceship exerts negligible gravitational attraction to him, the net force acting on the astronaut once he is out of the spaceship is zero. By the first law of motion, the acceleration of the astronaut is also zero. Newton's, now the next main topic is Newton's second law of motion, topic 4.5 basically, but I will not be doing it right now. I will be continuing it in my next class.